So, good morning. Hey, here we are again with 5 seconds delay, pretty much. And coffee. Are you guys getting me well? Okay. Better like this? Did it get better? No. I lowered it a bit because yesterday I was clipping quite a lot in some parts, but should be okay. Let's try shaders. It's a complicated subject to cover in one day, of course, and there's a lot to it. So this will be sort of just an introduction, and we're actually going to try to cover both GLSL, which is a low-level shader language. So just, well, not low-level, is low-level because it's a shader language, but it gets compiled directly to the GPU. And we're going to try out a much higher level tool of Unity, the shader graph, which is basically kind of something that mashes up different pre-built shaders, and that you can kind of connect them together and have very simple tools that you can create something that is quite advanced with very little effort. But first I'll try to just give a very quick introduction of what shaders are and what they're used for, and what types of shaders there are. And in practice, we're only going to cover one type of shaders today, and there is a few others, of course. We're going to only cover vertex shaders or fragment shaders. So those are shaders that kind of deal with 2D pixel data. So basically, they just deal with textures. Of course, you can make anything you want with a fragment shader, because if you have control over every pixel, you can also draw 3D shapes. You just have to be very good at figuring out what color each pixel is going to be, because that's what it's all about. So lots possible to do with these shaders. Of course, a combination of a vertex shader and a fragment shader is the most normal setup. And then there's a few more advanced types of shaders. We're going to go through all of them very quickly. But to really build, we're just going to build fragment shaders today. I hope we have enough time to make things clear. It's going to be slightly heavy on the math, but not really. I'm going to try to keep it really simple, because I think the most interesting thing is for you guys to have the tools set up. We'll have to set up a couple of tools as well to be able to code in GLSL, but they're easy to set up, very easy. And we're going to cover just the basics of what a shader is and how they work, and a few simple tricks to get something looking interesting. and how to explore when building a shader, how to kind of approach sort of the creative process of creating a shader. Um, um, it is lower level than what we're used to here. Is more math savvy than what we're used to. Um, it's but hopefully it will make sense, and you'll see like, oh, so this is what shaders are. This is how they work. It's really interesting to see how powerful graphics cards are, and especially when compared with CPUs in terms of processing power. Um, so that's something really impressive to see, and you can see it quite in a very simple way and very quickly when you start building a shader. And 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 my goal with this lesson is that you are aware of what shaders are, how to use them, and that it becomes less of black magic thing, so that you have then the more uh, courage to get into them and to really get a bit deeper into shader building. It's really a fascinating world. So let's see. Shaders. Shaders basically are a specific type of program that you code in specific languages, uh, and they are built for running on the GPU. So they run on your graphics card. So any program that runs on your graphics card, we just call it a shader. Right? Your graphics card as a processing unit, just like a CPU, but of course it's a GPU and it's a different architecture. Um, and um, and and any program you write that runs on the GPU is a shader. What shaders can do? Well, they are less generic than a CPU program. So with a CPU program, you can do a lot more variety of things, and they are much more intuitive to us because we're more used to writing programs for the CPU. Um, so the CPU is more like, okay, do this and then do that and then do that and then do that and then return this value back to me, or perform this action. Um, GPUs work in a highly parallel way. So when you're running a shader, you're mostly writing much less code, so very short amount of code, because you're writing the code for just one part. So, and that part depends on what type of shader you are doing. So for example, if you're writing a fragment shader, which is the ones that we're going to be looking at today, all your code is just defines what to do with one pixel. So you write code for one pixel, and that code runs parallel on the GPU to cover all the pixels of whatever it needs to cover. So it could be the full screen, it could be a window, it could be a part of a shape, of a 3D shape that's been textured with that shading. So you will be dealing with just one pixel, which makes things simple and also makes things complicated. It makes things simple because you only have to kind of think of one pixel in a way and just code for one pixel. So some things become really simple that are not so simple when you try to do it with a CPU tool, basically. Um, and um, and some other things become really complicated, because when you even just think of, like, I want to draw a square, but you're just coding for one pixel, then you need to think, how do I approach this, right? So I need to know some information, so where this pixel is on the screen, and is this pixel within my square? If it is within my square, paint it one color. If it is outside of my square, then paint it another color, right? There's also differences in style. So the style of coding is different, mostly because of performance. There are things that GPUs do really well, and there are things that make their life hard. For example, if statements. You normally don't. You need to avoid if statements at all costs. Although you have them and they work the same. They basically work the same way as in a CPU language, but they block the parallel execution of all the pixels. It's really a low performance thing. So mostly we don't use if statements. We need to navigate around them, which is a little bit weird because we're so used to if this then that, right? So that's how we've been coding all this time. And now we need to think about mostly about maths, because maths are the big power of GPUs. Like GPUs can do maths really fast. So types of shaders. We have fragment shaders. Historically, that was all there was in the beginning. So those are basically a way of the graphics card to deal with each pixel. So for a fragment shader, you code for one pixel, like I explained before. And then that code runs for all the pixels that it needs to run. And the same code runs on all the pixels. And all the pixels are run in parallel, with at least with very high parallel processing. So so a lot of those pixels are going to be running at the same time. So you also need to keep that in mind. And then the only thing you need to do is to write one function, which is the function that sets a specific color for that pixel. So you just need to make a decision of a color, and it's all about that. Just decide what color this pixel is going to be. There are vertex shaders. Those deal with 3D shapes, and the code runs for each vertex or vertex. I always screw up that word. So they run for each vertex of your 3D shape, of a 3D model. So you input a 3D model, and then it runs for each vertex of that 3D model. And then normally what it does is that sends that output to a fragment shader that then it renders it on the screen. So in a vertex shader, you can do operations on the 3D world. On a vertex shader, you do operations on a vertex shader you do operations on the 3D world. On a fragment shader, you do operations on each pixel, basically. Let me just turn on my switcher that I forgot. Okay, so let's see. So we have vertex shaders. Vertex shaders, and they work. And they do. Oh, I suck at drawing, so be aware. Plus, I was looking at the wrong. Ooh, my tablet is. Wait a second. There we go. There we go. Oh man. There. More or less. Let's actually make it in triangles. Today I'm especially bad. There we go. So vertex shader is code that runs for each vertex of your 3D shape. And it can do operations on them. It can decide on UV coordinates, so where the texture is going to be applied on it. It can actually move vertices, so you could say, hey, this vertex actually moves here. So the CPU sends it the 3D model, and it gets it, and when it's going to be time to render it, it can do operations on each vertex. So you could say like, oh, move it in a random direction a little bit, move this one there, and move this one here, and then you get like a little bit of noise on your model. So you could do stuff like that. This would be like the most simple thing. And then this one sends, give me a second, so, why did it, yeah, there we go. So this one sends information to the fragment shader. The fragment shader, and the fragment shader works on each pixel. So this one will have always a rectangular output. We don't know how many pixels there's gonna be, but there's gonna be a bunch of them. Okay, drawing is getting better a little bit. Still not an artwork. So then a fragment shader is going to make an operation for each pixel and choose the color. So you write the code to choose the color of one pixel. That code runs for all the pixels. You can send extra information from here, and you can send also extra information from the CPU. So that's your CPU program here. Let me see if I can move it. No. Doesn't matter. So your CPU will send information through the 3D model, but also it can send any type of information. It can also send it directly there. The CPU can inform these with whatever you want, like any data that you want to pass in there. You can pass, could be, for example, the position of the mouse, let's say, or the time, or the resolution of the screen. All that information can come from the CPU into your fragment shader or into your vertex shader, and then that is built into like a pipeline that just ends up in the fragment shader being sent to the result of the fragment shader being sent to your screen, and then it just runs on your screen. There are a few other types of shaders. For example, wait a second. For example, there's geometry shaders, and geometry shaders are used for example, what is it called again? I forgot the name. Like primitives, yeah. So geometry shaders deal with primitives. What happened when I moved here? It becomes blue. That's interesting. Okay. So geometry shaders deal with primitives, and they can actually add geometry, and they can add vertices if you want. So you can kind of increase the level of detail of of an object. There are tessellation shaders that can subdivide shapes so that you get more detail, and those are very used to 3D models to create like much higher poly counts on real-time applications, and especially you can tessellate differently as something gets closer to the camera. So you could have the same model, instead of having LODs, which we normally do, that we have like uh, a level of detail for when you're really close to it, and then as you get further away from the camera, you switch that model to another model that has a lower poly count. But let me just see what's happening here. There we go. I'm just checking if there's any stuff here. Yeah. So, I was talking about tessellation. So instead of LODs that you kind of switch the model to a lower resolution, you actually can, within the same model, the parts that are closer to you get more detail into them. So within the same model, you could kind of get a very detailed version close to you and a lower detailed version further away from you. So we've talked about vertex, fragment, geometry shaders, tessellation shaders, and the last one would be compute shaders, which just do maths, right? Because the GPU is super good at making a lot of complicated maths really, really fast. Compute shaders are useful sometimes when you don't need to render anything, but you want to just use that power and make some maths. That would be, for example, they use for Bitcoin mining and so on, right? So those are compute shaders. Of course, they don't just do mining; they do a lot of other stuff, also within programs and games. So those are the types of shader. Is that clear? And am I forgetting something? Guys, are you there? Good. That was the delay. So still have to get used to the delay. There we go. That's what shaders are. So you got your program, your CPU program. Your CPU program sends stuff to your shaders, and then your shaders decide how to either move your geometry or paint your pixels on the screen ultimately. And we're going to start learning about a bunch of just basically one language that we're going to learn, and the shader graph, which you can consider a language or just a tool. So today we're going to be talking about GLSL. GLSL stands for OpenGL, or GL from graphics library. So OpenGL is a open source project graphics library, and this is part of that project. So is OpenGL shader language, and that's what it stands for. There's also another language called HLSL. They're very similar to each other, and they do pretty much the same thing. The syntax is slightly different. And this one is part of the DirectX program, so that's from Microsoft, and it stands for High Level Shader Language. We're going to focus on this one. There is also a third language that is a higher level to these two, and that's actually what Unity uses if you want to write shaders in Unity, and that is called CG, which means C for graphics. And actually this compiles into one of these two, or both. So that's why Unity uses it, because this one is basically very similar to both, but it just bridges the difference between them, and you can compile CG into GLSL and into HLSL. Okay. Why are we going for GLSL? In this case, just because I have much more experience with it, and it's much easier for me to get you guys up to speed on a very simple way. But also because it's very easy to set up stuff, because this is open source and it's not so this one HLSL mostly runs just on Windows. This one runs on all the platforms, including mobile phones, so you can get shaders running on your mobile phone very easily, and that's a fun thing to do. That's how I fixed my my broken screen. As you can see, like, my screen has a pink line in there that is that because it just fell and it broke, and there's a crazy breakage there. So then I wrote a shader that just makes it into a fun little animation thing. See? Runs on your phone. And it's exactly the same code. Runs on the phone, runs on the computer, runs on Linux, runs on everywhere. So that's why I chose this one. Of course, this code also runs everywhere because it compiles into GLSL, but this one needs to be compiled into one language and then into the CPU, and this one just goes straight to the CPU, so it's a little bit easier. We're going to be installing a couple of things, and I'm gonna tell them to you right now so that we can start. And I wanted to kind of do this outside of Unity first, just because it's kind of simpler and easier to and more direct, because it's very bare bones and you see the result right away. And we're going to be using very simple tools, and then maybe on the afternoon we try a slightly more advanced tool, quite more advanced tool. So in this case, one of my favorite tools to code shaders on is actually just the text editor, the code editor, Atom. I don't know if you guys have it, but if you don't have it, you can just now is the moment to go and download it. It's quite small and easy to download, so it shouldn't take a lot of your time right now to download it very quickly. If you already have it, then great. And basically, Atom is it's a code editor. It's made by the GitHub team, and it works works very similar to, for example, Visual Studio Code, which is actually made by exactly the same team in exactly the same technology. And it works, it's easily extendable with packages, so it's open source, and you can install extra packages to it. And there's a few packages that allow you to code and preview, or actually just view, because not really a preview, it's an actual view just to run the shaders. And to run the shaders directly within the editor in quite nice ways. So there's a few extensions we're going to install for Atom. So now's the moment to go install Atom. And then we're going to go into which packages we're going to use. Is it all clear until now? Is there questions about the high level explanation of what shaders are? And Atom. It's Atom. You can download it from. Let me see if I can show you here. Give me a second. So actually I'll give you also a few. Let me just open a couple. Let me just switch this to webcam. There we go. And then let me just give you a few resources, and I can show them to you. Atom. So the Atom website is atom.io, and you have right on the front page a let me see if I can get it to browser. Let's see if it shares the browser. Yes, there we go. So that's Atom. You can just download with the button. For your platform gets chosen for you automatically, so easy. Resources for shaders. There's a couple of things that become a problem when you're searching for both inspiration and information in general about shaders and documentation especially. There's a couple of problems with it. So first, it's a very niche world. A lot of people that are really good at maths that assume that you know more than what you probably know. So the documentation can be a little bit dense, to say the least. One good place to start is actually just Wikipedia. It explains all the types of shaders, so whenever you so there's a bunch of different types: primitive shaders, compute shaders, tessellation shaders, geometry shaders, vertex shaders, and so on. Pixel shaders were an old version of the vertex shader, the fragment shaders. So those are fragment shaders. It's just different ways to call them. Also about the languages that are around. Here's the HLSL, GLSL, CG. So if you want to review all that stuff that I've been talking about, just the Wikipedia page is actually a really good way to start. Then there is a couple of other resources that I will post in the end on the description. I'll talk about them here. I'll leave these tabs open, and then I'll share them on the description of this video when I record it in the end. Wow, that's such a YouTuber thing to say. I just realized. Uh, um, and we're going to be using Atom with a few packages. You can install the packages within Atom itself. Um, and like I was saying, so the documentation can be a little bit dense. You can find the full documentation of GLSL by just simply Googling GLSL documentation. You probably get straight to it. With the Khronos group, and that's really dense. So this is a spec, so that's even more dense. There is a reference pages. There we go. So here you get everything. This is the page you should be looking at when you are looking for stuff. And okay, so you get all the possible things here, all the possible functions and so on, and all the stuff that is available to you, all the tools. And then when you click on one of them, you get the description. So there's not so much like examples of the usage and so on. So the documentation is a little bit old school. So that is one problem. Another problem is actually Minecraft. So any search you do for shaders, when you're looking like, oh, what cool stuff people are doing, because shaders are like a thing that it's a little bit hard to kind of have, because it's something new that you start on a bit later when you're coding, and it's hard to kind of have something that inspires you. You need to learn different tricks to have like a portfolio of solutions in your brain, so that you can start trying to create stuff. And when you're looking at stuff, since Minecraft came, and they support basically writing shaders for Minecraft, so you can kind of do crazy stuff like these new ultra realistic Minecraft things with RTX shaders. So since they come up, they become incredibly viral, and a lot of people are getting into them. So whenever you look for resources or questions about shaders, or if you just Google shaders in general, just when you Google shader, you get Minecraft, 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 Minecraft. All the results are Minecraft. So even on the description of Google, what you see is Minecraft. So it completely took over, because it was a very niche community before, and now just came this like huge monster of Minecraft. Which I'm not kind of dissing Minecraft. Minecraft is fine. I'm just saying that it just overpopulated, and it hid all the documentation on actual shaders that are outside of Minecraft. So that is one of the big issues, that when you're looking for stuff that you want to make a shader that is not a Minecraft shader, then it's very hard to find anything, because you'll find like 3,000 Minecraft results for one actual shader result. So I will try to put a few of the things that I found on the description of this video. I don't have them ready right now. A few of them I will mention, because they are really nice resources and really easy to follow and really well made. But then the others, I will just put them in there. And then you can check them later on. So one of them I'm also using this time, so you guys can install Atom. Let me know when you guys are done. which I'm guessing a few of you should already be done. There is one resource that I find extremely well done, which is the shader book. No, the book of shaders, actually. The book of shaders, which is an online book. And it's free, so guys, it doesn't cover everything. So all these stuff are stuff that are on the table of contents, but they're not yet done because the author is kind of actively writing it. Sort of, it's been there for many years, so I don't know if he's still actively writing it or if it just stayed like this. But at least for the basics, and from here, like what is a shader, hello world, uniforms, this is a really, really nice thing to start. And I wish I had it when I started. I found it quite late when I was already kind of into all this stuff by digging into the really, really thick documentation and reference of the Chronos group. And this just makes your life so much easier. So this book is great, and it is awesome also because shaders also, of course, run on the browser very well these days. It has a bunch of examples, and all these examples are interactive, so you can actually code within the site. So you can change the code. You can change the code and say, and even have like little widgets to change values. So if you can choose colors, you can change anything on the code and it just updates here. This is the result of the shader basically. So that's really cool. This book of shaders is really, really a nice thing, and actually it's on a bunch of languages as well, so that's really cool. I don't know if they're complete. I've never checked any of the languages besides English. So Atom. Do you guys have Atom installed? Yeah, we have Atom. At least one. Yep, good. So when you install Atom, you should see something like this. This is Atom. It's a really nice, it's my primary coding tool. I'm doing a lot of stuff also with JetBrains writer, which I'm really happy with actually. Which I started because of Unity, of course, and because we have the license from school. And I quite enjoyed it, but I still don't release Atom. So it's my go-to tool when coding. And it has a little bit of a learning curve in terms of using, because it relies a lot on keyboard shortcuts. But also it uses it has a really good fuzzy search for everything. So that's really nice that you can just type whatever you want and it will find your tools for you. For that, you just need to press Control Shift P, Control Shift P, and then it opens this fuzzy search bar. And then there you can type anything. And if you want to install packages, for example, you can just say install, and then it finds all this stuff. And you can install packages and themes here. And if you click it, then you go into that. And here you can just search for a package and then hit install, and it installs, right? So the packages we're going to install are all under the search GLSL. And then if you search for GLSL, let me know if this is going fast and if you're not following or if you're still behind. So GLSL, and then the first thing you want to install is the language GLSL, so you get support for the language with the color, the code coloring and all that stuff. So that's really good to have. Then autocomplete GLSL, also very useful, of course. GLSL preview is the one that will be allowing you to see your shader running, and actually this is really nice because with shaders you get to they compile extremely fast, so you can actually be coding and seeing it at the same time. Like a lot of live coders, or most live coders, code shaders. So they are coding actually fragment shaders live in the clubs while the music is playing. They're coding, and well, those are very nerdy clubs, by the way. But so they are coding mostly GLSL. And generating the visuals live as they code, because they are you can be coding and the shader is automatically just updating every time you type anything on your editor, which is really cool. Also for debugging, it's really fast, and for developing and kind of doing this kind of very fast development thing. So basically it allows you to do Control-Shift-G, and Control-Shift-G will preview your shader, and then it will stay there, and as you change the code it will live change. Another thing you will want to install is the linter. That will give you error messages and all that stuff. That will be installed automatically if you install Vida, which is a really fun tool. It's not really necessary, but Vida is a VJing and live coding environment for GLSL. And what it does is that it allows you to go like full screen, to have the shader running on the background of your editor, so that you're coding on top of your visuals, so you can see the code and the visuals at the same time overlaid. And it has a little bit more powerful features than the GLSL preview. Also, it has a little bit of a different approach when it comes to the uniforms. We're going to talk about that. So your code actually needs to change slightly, but it's just a very slight change between this one and the GLSL, the GLSL preview. But it's fun to have. So if you want to install Vida, I'm going to show you how it works. So that's it. Once you install all of this, once you install it, they should install all, and some of them, like the linter and the linter GLSLify and a few others, are going to be installed as dependencies. So this is a package manager, so it will install other dependencies as needed. But the very basic is language GLSL, autocomplete GLSL, GLSL preview. At least these you should have. And then if you want specifically, Vida is a really nice tool and really fun to play with. So let me know if you have problems installing something, or if it's not working for you, or if you didn't manage to get into this screen, or any other thing. Just feel free to interrupt me. So once you have these things installed, we just need to create a new file. So this is actually an empty, untitled new file. And I'm going to just jump right in and try to, well, jump right in. We've been live for an hour, so it's about time to start actually coding. Yes, I think so. So the question is to change the location of the you mean of the packages? Uh, and did you install Atom in your C drive? So then, oh really? Oh, it should always give you options. So it installs the packages where Atom was installed. So if you install your Atom on the C drive, then all the packages are going to be installed on the C drive. But you should be able to move Atom installation to, or even have chosen on install moment, there must be a place where you can choose where you want to install Atom. I'm pretty sure it doesn't just force you to use C. I'm not sure how. Let me just try something here. Let me just basically Google that for you. Atom install location. So that is funny. I'm sure there was somewhere there that you missed an option to where to install it, because on all the installers should allow you to. Or did it install through? Yeah, did it install through the Microsoft Store? I don't think so. Let me just download it again here to see. No, it's just so it's just an installer. So for sure it needs to give you an option to where to install. So I'll move forward and then you let me know if that worked. In any case, this has been recorded and I'll share this later. So if you lose some part of it, you can always come back and review it. Coffee time. So enough talking. Let's get cracking. So shaders, GLSL. First thing I'm going to do is I'm going to save this. So I just click the new. It doesn't show the context menus on my stream. Okay, but basically this is just a new file. So I just found the file new and it's untitled. And I'm going to Control S to save it. I have a bunch of shaders here. I'm going to go into basic maybe and do my first shader, and I'm going to save that as a frag file. So my first shader.frag. .frag is the usual. Okay, you don't see that either. Let me switch to this so that you can see it. No. So I am just calling it .frag in the end. So I'm just saving that as .frag. Save. When you do that, if you have the things well installed, let me go back to this because then it's easier to see the code. You should see here on the bottom let me go without cam. There you go. So here on the bottom you should see GLSL. So if you see that, it's because your packages are well installed. Am I having problems with the feed? I'm seeing here that the connection is floating a bit. Let me know if it's working. Yeah, all right. So maybe it's just on my end. Okay. Yeah, because here I see everything like on my YouTube studio thing. I see it a little bit like a potato. Uh, it's like super low quality, and it's buffering all the time. So I don't know. Maybe it's my connection. If you guys see it well, I'm happy with it. So so if you see GLSL here on the bottom, that means that your installation is correct and you're ready to go. So let's start to write a shader, basically. And shaders have a few uh, particularities here, and everything that I do and say here can be different, or at least most. Wait. YouTube is complaining, so there is something wrong. YouTube is complaining that there's no smooth streaming. My connection is probably fluttering. I think I know what it is. Give me a second and I will fix that. Give me just 1 second, I'll be right back. So I'm back and I'm back. There was my kid was streaming cartoons, so she was occupying my bandwidth. So I just switched it to 4G. So now we're back, and now it seems to be working fine. Um, so so we were going to start writing. So the thing is, there's a bunch of versions of GLSL, and the logic is the same. The syntax changes, and some other things change as well, like the precision of your numbers and so on. So it always really depends like what code you write, and actually some differences are quite fundamental from version to version. So depending on which version of the language you're going to be writing, and that also depends on what is going to be running that language. So different frameworks require different versions. So that's a little bit of madness. So I want to stay away from that because it's boring and it's going to take a really long time to kind of go through the different versions. And let me see, it's 0. Do I have audio? YouTube keeps complaining about things. Yeah, okay. I'll just ignore YouTube for a bit. So there's all these things with versions, like that they change quite a lot from version to version. Some frameworks, like if you're working on open frameworks, for example, you have some versions that are available to you. If you're working on other programs, you have other versions. The newer versions actually changed quite a lot, but then they're also, because they changed quite a lot, their adoption with bigger frameworks is a bit tougher. So it takes a bit longer to be like implemented on other frameworks. It gets tricky with the versions. Just keep that in mind. I'm not going to go too much into detail with that, but things change from version to version depending on what you're using. So you just need to go and check on the documentation what the changes have been if something stops working. For now, that's also why I chose to do this in Atom, because then we can just ignore that, and if it works on the preview, then it works for us. And then we're going to get into try, at least, because actually I don't have it installed on Windows, but we're going to try to get into GLSL Viewer, which is an external tool. It's just a command line tool that you can run shaders in a bit more powerful way. And as a fun thing, I'll also show you how to run it on your phone, so that you can see how much powerful stuff you can do just with a small GPU of a phone. But all of these, I'm going to use a sort of a middle version of GLSL so that we can just be compatible with everything. But I'm going to just ignore version differences, and then just keep in mind that that is a thing. So basically, when you write a shader, you just write a function, right? There's no the whole OOP thing going on shaders. Is very, very, very imperative. So you're basically just going to write a function that sets one specific variable, and that function is always called void main, and there you go. So that's void main. That is the core of your shader. In this case, it's handy to put to set the precision here, because sometimes you get some problems. So we need, but by the way, the language is its own language. It's GLSL, and it's very similar to C. So it's based on C, but the native types are different. So we have much more options into native types, especially on matrices and vectors. But we're going to attack that as we go along and as we see them. Also, compiler tags like the if and def, that also is very similar to C. Oh, it's trying to autocomplete too much for me. So these are compiler directives. So the ones that start with a cardinal here. Actually, I want if def. I want to just set the precision of our floats, because that is a problem with versions. That is one of the main things that make a difference on your shader. And so what I'm going to do is I'm just going to put here, if it's defined GLES, oh Jesus Christ, GLES, I'm going to set the precision of medium P to float. And this seems weird, but you can just safely ignore it and just put it in there, and put it on all your shaders that we're going to do right now. Just have this. And that's something that happens a lot with shaders, because they are a little bit less reusable than the CPU code, because there's no like OOP architectures behind it. What people do is that you make a huge collection of snippets, right? So there's a bunch of snippet tools that you can use if you really write a lot of shaders. you'll have a bunch of snippets that you save on your atom. So basically that's just a big set of functions that you've written before to do things, and that you just have to copy paste from one code to another, because they're not reusable. You cannot just have like different files and all that stuff. So what you do normally is just you paste them into. Ooh, somebody got their speakers on. Yeah. Yeah, is this okay? Yeah, we're not writing. Okay. Uh, so, um, so, where was I? So yeah, basically what you're going to get is a lot of these little things, and actually full functions uh, that you're going to be storing on your collection of snippets, and then whenever you need them, you just copy paste them into your code. Stuff like, for example, generating random numbers. There is no that's going to be super weird for you guys, but there is no way to generate random numbers. There's not a function. You can just say random random range like on Unity. You actually need to write a function that generates random numbers. So you're probably just gonna write that once, save it on a file somewhere, and then have it to be able to copy paste into your code whenever you need a random number. So so people just collect a bunch of snippets. There is Atom packages that allow you to collect those snippets and then autocomplete for you when you select random, and then it just gives you the option to put your full function in there right away, and it saves your snippets and so on. I don't have it installed right now on my Windows machine. But just keep in mind that that's going to happen a lot, that there's stuff that is just, oh yeah, that's just the way it is, right? And you collect functions from somewhere, from online, from stuff that you've seen, from some stuff that you've tested and you liked, and then you just have to just keep track of your library of tools, basically, because it's much less reusable than the languages we're used to. So basically, the whole point of the void main function is to set one variable, and that variable is gl frag color. And this variable already exists. You don't need to define it. It's there, and when you set this to a caller, and this is of type vec4, and that's something that we need to talk about, which is types. But we're going to get into that in a bit, because I'm talking too much and it's getting boring. So vec4, and then it's basically like Unity vector 3, but then it's a 4. So that's does X, Y, Z, W, for example, or RGBA if you're working with that, or any other 4 float container, basically. So there's just 4 floats. So let's say I put 0. 0.0, 0.0, 0.0, 0.0. Whenever you have floats, you need the point in there. So even if you just put 0 point, that's fine, but you need the point in there. Let me put 1 here on the alpha. So this would be red, green, blue, alpha. Okay? In this case, of course, this would make a black screen. Right? So if you do Control-Shift-G to preview, you get a black screen. And that's your first shader. So all the pixels are being painted black. If you change that, for example, if you put 1 in here, boom, it's red. Right? If you put 1 in here, then boom, it's yellow. If you put 1 in here, then of course it gets white. Ta-da, that's what the shader is, right? So this will paint any pixel that is part of this shader rendering area, any pixel is just going to be painted white. So this is the simplest shader that you can write. So this code right now is running for each single pixel of this image over here. And basically that's as complicated as it gets. That's it, right? So you're just defining a color for each pixel. Now, from here on out, you just need to start getting creative and starting to get more information, of course, because if all the information you have is, okay, there is a pixel somewhere and I'm going to choose a color for it, it's very hard to figure out which color to use. But there's, of course, a few informations that you have. So, and plus you can send your own information from the program that is running the shader. In this case, the shader is being run by this GLSL preview app. And that GLSL preview app sends you already some information. So it sends you, for example, the resolution of the window, so how big the window is, and it sends you a variable of time so that you can do animations with it. And so this shader is already, like, it's painting all the thing white, and it's actually continuously running. So this runs for every frame of your screen refresh rate, so it just runs as fast as it can. So this is running from your graphics card continuously. So this could be an animation. It's just that it's an animation that is always the same frame, so you don't see anything moving. But this is already running, and it's running on a continuous fashion, so it's a loop. Let's see what other information we have available to us. So most of them start with GL underscore. So you see that I'm typing and I'm getting errors right away in here. That's the linter, and that's the shader trying to run as I type the code. And when it cannot run, of course, it gives you the errors so that you can see what's going on. But of course, these are errors because I'm in the middle of typing. GL underscore is the at least on this version of OpenGL, and there we go with the versions. It's the prefix for most of the built-in stuff. And you have GL layer, GL color, normal, vertex, fog coordinate, frag data, so that's the fragment data, GL position. There's a bunch of stuff. These are about either vertices. There's a million things. So GL frag color, that's the one that we are setting. Some of them you can set, some of them you can read. One interesting one is this GL frag coordinate. GL frag coordinate tells you where on the screen is this pixel. So which pixel is this on your image? So we could use this to influence which color we're going to be selecting here. But the thing is, this is in pixels, of course, and this goes from 0 to 1. So 1, 1, 1 is white. That means that 1 is the maximum value you can have for a color. So that if we use this directly, then we would have a little bit of a problem here, because after the first pixel, everything would be over. So everything would just be white anyway. So it's normally a really handy thing to have is to divide this by the resolution, and then the resolution will, so this will be like from 0, 0, which is 0 on this corner, from 0, 0 up to 1, 1 on this corner over here. So that would go from 0 to 1. And so that would be really handy, because then we can do stuff on the whole screen. But for that, we need to know the resolution. And to know that, the GLSL program, the GLSL preview program, sends us that as a uniform. And uniform are uniforms are things. Let me just comment this one out to see if everything's okay. Wait, I forgot to say that it's a vec2, of course. So that's the resolution. This program sends you a few uniforms, and uniforms are things that from your CPU program, from the stuff that you're coding and you're going to use this shader on, you can send information in. And in this case, it's a vector2. It's a vector2 resolution that has x and y, and x is, of course, the size in the width, and y is the size from the bottom all the way to the top. Keep in mind that the 0, 0 point is here on the corner. So this is the full resolution. So if you say here and you create another vector2, and let's call it chord, is equal to glfrag chord x, y. This is another thing that is specific to this language that I will explain, divided by U resolution xy. So this is how vectors work. So our vectors, they work pretty much as in Unity, that you can do .x and that works. But you have much more powerful tools because vectors are native to the language. You have much more tools, and it's much nicer to work with, much more direct. So you can do things like, if you have a vector4, vector4 test is equal to so let's just do it here so that I can. So imagine that you have a vector4 test. Let's actually create a color vector4. You call it color and say that it's equal to a new vector4 that's like the constructor sort of vector4, and then you send 4 numbers: 1.0, 1.0, 1.0, 1.0. Okay, so then we could say here that we set this to color. Okay, that works exactly the same way. So now we have a vector4 here. But the cool thing is that you can do color.x, and of course that's going to give you this value over here, 1. Wait a second. You could do y, and that will give you this value, of course, and so on. You could do z, you could do w to get either of these values. You could also do r, and that will give you the red value. You could also do g. So whatever you're using that vector for, so if you're using that for colors, you can use RGB, or you can use X, Y, Z, W. You can so there's a bunch of different ways you can call the same value, and it doesn't matter which one you use. It's up to you. It's just convenience. That basically doing color.x is the same thing as doing color.r. So x and red is the same thing, the same value. And also, you can convert, for example, a vector4 into a vector2 by just saying, I want the value of x and the value of y. So this will be a vector2 with these two values. You could say x, y, z, and you get the 3. You could even switch the order and say z, y, x, for example, and you get a vector3 that has first the z as the x of the new vector, then the y, and then the x. So you can just change the order, and you can do any combination here. You could do ARBG, for example. This would be the same vector, but then switching all these variables around. So you have all this freedom. So what I'm doing here is that I'm getting the x and y of the coordinates, so the x and y coordinate on the screen, and dividing it by the x and y of the resolution. That means that I will have a coordinate that tells me where this pixel is in proportion to the screen. So this would be 0, this would be 0, 0 in this corner over here, and this would be 1, 1 in this corner over here. So now, a little pause. Is this super weird and complicated? I see that you guys are already one step ahead, so I'm guessing it's not too complicated, but maybe for some of you it's getting really weird. Yes. Autocomplete sometimes gets weird. I'm not sure. I'm guessing it might be the... Yes? Sorry? Again? Ah, of course, you have the thing. So that I was going to call the break-in right now, actually. I just wanted very quickly to... Yeah, that's what I want. So it's break time, and you have now 1 hour, right, of the Ondernemerschap thing. So okay, so let's leave it at this, and then we come back to it. And the stream will continue in the afternoon, and then we'll start doing more interesting stuff. I see that you guys are doing already gradients and stuff, which is pretty cool. So that would be the next step. All right, so good. See you guys in a bit. Hey guys, I'm back. So is it all working? Yeah, seems to be all. We're back on. So back after the quite long break. We were here, so we had still just a white screen. I see that you guys are already experimenting with a lot more stuff, and it's looking cool. Great job, Quinn. That looks super awesome. To see the preview, you need to press Control-Shift-G, or then use your... if you have any doubts how to see stuff, how to use stuff on Atom, always the go-to shortcut is Control-Shift-P. That gives you a context menu, and then you can try to type what you're looking for. So if you're looking for preview, then you get GLSL preview, and it tells you also there the possible shortcuts that you can use right away. So there's always two ways to do stuff. So I see you guys going already quite advanced with it, so I'm going to move a little bit faster. Also because now we got the idea, is kind of see what's possible to do and how to go forward. So what we were was that we're receiving a uniform. That's information that is passed to us by the program that is sending the shader to the GPU. So this specific GLSL preview sends us a resolution uniform called uResolution. The name needs to be that, or else it won't work. And it's a vector 2, and that basically tells us how big our window is. Most platforms by default send this. If you're writing your own stuff, like if you're doing like bare bones like C++, or if you're doing it for the web as well with the WebGL and stuff, you will need to send your own uniforms. So you'll just have to check the size of your canvas or check your size of your window and then send it to the shader. And there's always a different way to do it with every platform, depending on what you're using. If you're using OpenGL, if you're on a framework on top of OpenGL like OpenFrameworks, if you're just doing WebGL with JavaScript, so on. Every language has a different way, so you just need to check the documentation of the language you're using for your CPU program to see how you can connect that to your GPU and send uniforms. But basically you can send uniforms of any type that the GLSL accepts. So vector 2s, vector 3s, vector 4s, matrices, floats, and any. Now we're getting the resolution, and here we know that the frag coordinate tells us which pixel we're dealing with on the image, and we're dividing it by the resolution so that we get a coordinate that goes from 0 to 1. So then we can use it directly on colors. So if I was to do coord.x here, then the red, let's actually put 0 on the others so that we only see the red, and 1 on the alpha so that the transparency is not there. So we see that the coordinate goes from 0 on the bottom of the x, and it goes up all the way to 1, which is full red on this side. So now we have like a nice gradient here, and you can just do the same thing, like for example for the y, and you could say like, okay, now here I do coord.y, and then now you have an even kind of fancier gradient that mixes red on the x, so here is 0 red and here is full red, and then you get 0 green on the bottom and full green on top. So it mixes green, red, and of course the mix of the two, which is yellow. So that also tells you about the coordinate value here, and it makes it very clear that this is the point 0, 0 where everything is black. This is the point 1, 1 where both x and y are at value 1. Okay. If we hadn't done this, so if we hadn't divided by the resolution, then what we would get is that we get just one line of 1 pixel here. That's the 0 line. That is, you probably won't see it, but if you see it on your own screens, then you have a 1 pixel red line here and 1 pixel green here, and everything else is yellow because every value is above 1. So if a value is above 1, it gets clamped to 1 if you're dealing with a color. So then you just get full green, full red on all your screen except the first pixel where it's 0. So that's why it's handy to divide by the resolution, so you get values from 0 to 1, and those are easier to handle. That's what we do here. Now let's start playing with animation. Let's try to animate this and start getting interesting. Another uniform that you can send is the current time, because like I said, this is already running at a specific frame rate that your system is requiring, and your and your graphics card is handling. Of course, if your graphics card gets slower, then you get less frame rate. You know how it goes. So this is already running continuously and running this function for each pixel of your screen in real time, basically. But we're always sending the same color for the same pixel. So now let's try to start changing that with time. So there is another uniform that most platforms give you right away, which is a float u time. By the way, these names are sort of a convention. A lot of platforms use them like that, like u underscore, that means uniform, and then resolution, time, and so on. You can get like mouse position, stuff like that, depends on which platform you are. But they are not set in stone, so they change. For example, if you want to use Vida, the one that we Vida or Veda, I don't know how to pronounce it, how the makers intended it to be. If you use Vida, for example, then they don't use the U, so then you have to change your code to get just resolution and just time, but then the values are actually the same. So now we have time here. So now we can start using this. This will be just basically the time that your shader has been running, right? So when your shader first runs, then U time is going to be 0, and then it just keeps on going forward in seconds. But of course, it counts much faster in the seconds, so it's a floating point number. So you can get 0.0001. Well, maybe not so many zeros because that's really, really fast. But you get the point. U time is a number that just goes forward infinitely. So we could now try to implement that time here somewhere. Let's actually do here, because we still have the blue color that we're not using. Let's try to let's try to do that. So we have something that just keeps on going forward. So after 1 second, the value is going to be bigger than 1. So it's not useful for us to put it here directly, although we could. And that just means that blue is going to be always on the maximum value. But what we could do is use our old trick of making it into a function that repeats itself through time. So that would be, for example, a cosine and a sine are good old friends. So if you say that is the cosine of time, you get a little animation already going on. See that it goes up and down. Of course, as you know, the cosine of anything goes between -1 and 1. So there is this moment where nothing is happening, is when we are in negative values. So the blue is completely 0. And then we have this moment where it goes over 0 and it starts getting bluer, and then it gets to full blue and then comes all the way back again and then goes again into the negative. So if you want this to go, actually we can see that very easily by just putting these to 0. So now you have just the blue part going on, and that's just the full screen going on blue and back, and then it stays black for a while it's on the negative side, and then it comes back to the positive side and the blue is there. So so we put our fancy thing back, and let's try to just transform this very quickly into something that just goes from 0 to 1 and back. Oof, I have an animal attacking me. So then if we're going from -1 to 1, obviously we can just, if we add 0.5 and then, wait a second, sorry. So we're multiplying that by 0.5 or dividing by 2, that's the same thing. that means that it goes from minus 0.5 to 0.5, and then if we add 1, then we go from 0 to 1. So now if you put these to 0, then you can see the result, and we should see that it goes from black to blue, 0, it goes from black to blue and back. There we go. Oh, actually it's not going from black to, it's going up to high because it's plus 0.5, and I'm comma. Wow, there's a dot here. Okay, there we go. Now we're going. So you have to reduce it and then move it 0.5, of course. So now it goes from 0 to 1. It's always good to test because no matter how confident you are. Sorry. I'm a noob streamer, so I forget to look at the chat. Let me just... you can say your questions, it's fine. So question on the chat. I have the precision on number 2. That person that works for me, but when so you get an error here on this part. Is that the problem, or on the precision? Yeah. Oh, that's weird. Might be some versioning issue, but actually what you can do is you can remove it, and it still works. It's the same. So just remove it. Yeah, this is just so that it works in multiple platforms. So if something is going wrong in there, then wait, no, it's actually now complaining to me. So it does need it. For me, at least, it needs it. So what kind of errors are you getting on the precision when you get the right... Yeah. Make sure you have exactly the right code. Medium P, there's a P in there. And then float. Is that correct? And you still get the error 4 times. Interesting. Try to remove the definition. Oh, sorry. Remove the if def and the end if. So maybe it always sets up the precision. See if that works for you. Okay, then you can just keep it like that and always have the same precision. So, well, this will give you less precision all the time, but that's fine for now. Now, so let's see, what else can we do here? So now we have like a fancy animated thing. We could try to animate all of them, of course, to just go and just get all of these into something. I'm just gonna paste the same value on all of them, so you get like black to white, and then of course you can start offsetting them, the good old trick of just doing like 0.9 for example, and then the red is going at a slightly different speed. This one you can maybe even divide by 2 dot, then you get this thing. But now we're still getting now full screen, the same color, because we're getting the same pixel. We're not using the coordinates all the time. We could say, for example, we could just add the coordinate. So you can just play with the numbers, even like random changes there. they will always do something. And because you have like this instant feedback, it's really easy to just be trying things out and just like try adding, try multiplying. So if you add and it's like, okay, now we get this thing going on, which is pretty cool. But what if I multiply instead? So that will do something else, right? So that's pretty cool as well. And then you start very easily start, let me just see, I need to make this a little bit small so that we can see the code. So you see that very quickly you start getting kind of weird, interesting results. And if you then start reducing stuff or making them really small, you see, so see, this is like a cosine wave going up, a cosine wave going there, and the blue is doing the full screen blue pulse. And of course you can so the more you play with this, you're just gonna start getting, you see, like, because because we're using the time, the cosine of time, then of course we get also in time we get this zoom in, zoom out effect. And mostly it's just like the more you learn is the more you play. So you just have to try things out and you start seeing it happen, and then you try to understand why is this happening, right? And how can I make it even more weird? And the weirder it gets, the more things you'll start seeing, and then you want to start controlling them. But it's okay to not have control over what you're doing. It's absolutely fine to just play with it. It's an awesome toy to learn maths and to understand how these calculations work. You can just, of course, switch cosines to sines, and then you start getting different colors in there. And we're just still basically on 2 lines of code, because we could put this in here directly, right? So this will be just 2 lines of code, and you're doing quite a cool, interesting animation that it would be really hard to do with and if you add one with the other one, maybe even add the 2 of them. So these are pretty cool things that you can do. On the stream, I guess this will look a bit weird because of the compression of the video. But you can like it's okay to not want to control exactly what you do for a while until you start actually figuring out things and saying like, oh, okay, so this is a cool trick, that's another cool trick. And this is like a really cool result, and it's something that would be super hard to do on the CPU because you have to calculate every pixel. So even just making a gradient, that's a nice thing that I normally do. Is if I'm on another context where we're like working with processing, for example, I try to do this with a CPU, and immediately you see that even for a low resolution like this, you get your performance starts going down if you try to calculate the color for each pixel one at a time, because pixels kind of they grow, right? Like as your resolution goes up, your pixels really go up. So so if you're running this on a full screen 4K screen, it's nothing for a shader, because most of them are like, or even all of them are going to be calculated parallel. So it takes as much time as 1 pixel almost. And to do this on a CPU, you'd get a few million calculations, all one at a time. So then you run into performance issues really quickly. And as you see, this runs like completely smooth, and it's no problem at all for the shader to do something like this. And that's where you start so then that's when you start kind of understanding the power of the GPU and how awesome it is to be able to have all that power to just control every single pixel on the screen. Another thing is that once you start realizing that, hey, I can control every single pixel on the screen. So if I have enough knowledge or creativity to figure out what color each pixel is on any image or anything that is in my brain, then I can make it, because you have full control of every pixel, right? So it's like there's no lower level than that. So you can draw pretty much anything you can imagine. It's just that it's harder to define things mathematically than to just say like, oh, I want a square right here and a square right there. So there is, Baris, you had a question. Could you make holograms with this? Yes, you can make holograms. Oh, of course you can make holograms. Not real holograms, unfortunately. No one can make real holograms with any technology yet. But you can make stuff that looks like holograms, yeah. Especially in Unity, we're going to go into shader graph, and then we can kind of see, oh, there's a million examples of holograms. That's kind of the classic. But right now, we're just kind of doing pretty stuff. So then, this is one trick. This is going really fast, and it's probably going to make us nauseous after a while. So I'm going to divide this a little bit more, just so that we have a little bit of a slower paced thing, so that we don't get any epileptic seizures. So this is the basic. This is the base of all shaders. And then from here on, it's all tricks. Okay, so that's it's just like figuring out different ways to calculate this, and messing up the coordinates, for example. That's a very common trick, right? So you can figure out like this, as you are doing now, the color of each pixel depending on their position on the screen, which is calculated by the coordinate. But then you can also just say, hey, I will fake this coordinate. So I will tell the program now that this pixel is not here, but it's here somewhere in the middle. So then you can do full transformations on the pixel base. So you can move pixels around and just shuffle these pixels around, right? And the way that you shuffle these pixels around can really give you interesting results. Well, maybe I can show you an example. So maybe like just with like doing rotations, for example, you can do something like, let me see if I have any, yeah, here, like this smoke frag. So, well, here you can see that there's a bunch more code, but it's not crazy. And you see that you get, and this is basically the same gradient that we had, or very similar gradient going on, but then I'm just kind of using noise functions to do sort of semi-random rotations on the pixels. So the pixel that should be here goes there, the pixel that should be there goes there, and then I darken some parts of them by just reducing the opacity of the pixel as well with some noise. So then you can use noise, and you can use a bunch of different things to do kind of pretty cool stuff. So let's go back to our regular code. So that's another cool trick. Let's try to do that. So with rotations, if you want to kind of do rotations within your pixels and or translations as well. So translation means to move stuff from one place to another. Rotations is to actually rotate it from the pivot point, which would be the 0, 0, right, in this case. So you can do 3 types of operations with matrices, which what we call matrix transformations, which would be scale, to just zoom in and out. You can rotate, and you can translate and move it around. Okay, so these 3. You need to also be careful that these 3, the order that you do them is very important, right? Because once you translate something, like your whole coordinate system is going to move. So then when you rotate it, your pivot point is going to be a different one. So if you first translate and then you rotate, then your pivot point is going to be translated first. If you rotate first, then you're going to rotate on the 0, 0 and then move it around. So that's a different thing. So you get a different result. So, but all of these, unfortunately, you need to code yourself, and you need to know about matrix transformations, and that math is a little bit boring to get into. But of course, there is functions written everywhere for you, and you can just find them around. And they're not really that complicated, but they are a little bit hard to understand and beyond the scope of this lesson, because or else we wouldn't really have enough time to do anything interesting. And I didn't really talk about shader graph, and we still have like only an hour to go, so this is already taking way too long. So what I'm going to do, I'm just going to write very quickly here a function to do a rotation so that we can play with it a little bit, and that's something that you can keep for yourself and use it on pretty much all your shaders, because this is a function that you see a lot. So it's just rotate, let's call it rotate 2D, and it receives an angle. That's actually it's a float, of course. I'll call it angle like this. And then I'm going to return this mat2 means that it's a matrix. It's a 2 by 2 matrix. So I'm going to return a matrix that is rotated by that here, rotated by that, and that rotated by a specific angle, basically. And that angle, of course, is in radians. So that would be the cosine of angle, and then the minus sine of angle, if I'm not. And then let me just put another line here. That's easier to read when you're making matrices. It's easier if you put them in actual format that they go, but it's the same if you put them in one line. Syntactically is the same. Sine of angle, but it's easier to think about it when you cosine of angle. And you see that the sines and the cosines come back all the time. So that is kind of the most useful tool you can have. Oh, I forgot one comma here. There we go. So now this should make a rotation. If you multiply this by your coordinate, then you get a rotation on that angle. So you multiply this matrix by coordinate, and you get that rotation. So let's try to do that and say that, and it's going to rotate like from this point, it's going to rotate it around. So I can try to draw that, maybe it's easier. Oh, I didn't turn on my switcher. Okay, so now, yeah. So that. So let's imagine you have your screen, and this is 0.00 here. And if you do a rotation of let's say 45 degrees, you'll get 45 degrees. Of course, this would be in radians, but it's easier to talk in degrees for us. So then you'll get like a rotation like this, and your screen would be like that. Right, so this is what you're doing. But of course, this is every pixel. So this if you rotate only this pixel over here that was there, this pixel is now going to be here. Okay, and of course this works as an infinite canvas. Of course, I'm showing you here the limits of our image, but for the shader it doesn't matter. This continues infinitely. So the pixel that would be the pixel that will actually be drawn here is the pixel that would be like somewhere there calculated, right? So then that goes there, so this one goes here, right? So the pixel that would be here is now going to be drawn outside of the screen, so it's not even going to show up. And the pixel that would be drawn here that was not showing up is now going to be visible here, right? So so that's what the rotation does. That's what this rotate function does. So let's try to do a rotation here and say that the coordinate is going to be equal to, let me see if there's any questions. Is this it's okay for you guys? Is it getting very complicated? Let me see, wait for the... Well, I'm guessing... Ah, the scene switcher is not switching correctly. Sorry. I'm going back here manually. So the coordinates is going to be the rotation. So rotate to the of a specific angle. Let's say, for example, well, let's use the time as well, so that we start rotating weird stuff. So let's say the cosine, let's do the same thing over and over again so that we don't have to introduce too many things, of the time. Okay, let's do it like this. Sorry, I'm backtracking on myself because I was trying to think like, okay, maybe we should do first a specific number so that we don't have the animation, but the animation actually makes it probably more clear what's happening. So of time, so then that goes from -1 to 1. Let's just do that times 2 maybe, just to have a little bit of a bigger range. And then times coordinate. So that will change the coordinate and rotate it around. So now you see that our animation is going on, but then it's also, you see that it's kind of rotating through. Sometimes you see it passing sort of, so that this is actually going, rotating like that. Actually it's going whoop, 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 right there. So it's rotating to one side and then back, and then one side and then back, because it's a cosine, so it's the cosine of time. So it's doing that. It becomes clearer probably if you have these lines going on that we had before. So now you can see it rotating, right? So that's pretty crazy. Let's actually reduce this and reduce this one as well, and multiply this one as well. Woo, that's going very crazy. Let's divide this to make it slower. Let's divide this by 0.2. Oh, actually, that's quicker, of course. That should be slower indeed, but we're getting really psychedelic really fast. 0.2, and let's try to maybe not multiply by 2. It's going so fast. Let me just close this so you can see the more code. Like that. Like that's better. So wait a second. The cosine of time is going really. Let me just do this so that we start from 0. Times. So we're getting because these are also the cosines of time. So let me make something a little bit clearer. Let me stop that rotation for a second. Ooh, much nicer. And now, so that we see what we're doing. So that's good. I'm gonna remove the time from here. Let me just try to do that. So then we have just one type of lines, for example. This one's fine. And this one. Or 0, 0, 1. That is, whoa, that's cool. 0.1, 0.2 was nice actually. That might be easier to see. And then if you do the rotation, I'm completely inventing here, so bear with me for a second. And then let's do just the time. That is, of course, really, really fast and going back and forth. If we divide by 100 dot, then we get a much slower thing. And now you can see the rotation. I don't know if you see it on the stream because it might look like a solid color pretty much. But there is little lines rotating around if you don't see it. But if you try it on your own, then you'll see that they are kind of rotating around like this. If you do maybe even 200, so that is a little bit slower. Oh, what? Autocomplete is. There we go. Now you can probably see on the stream much better. Yeah, so stuff like that. And now we're doing like a rotation that doesn't depend on the coordinate itself. So it's always kind of is rotating the whole canvas basically. We're doing a full transformation on our whole canvas. But you can do it per pixel, of course, because this is just one pixel. So you could make a different rotation for each, let's say for each coordinate dot x, and then you start getting much weirder stuff. Not coordinate. There we go. So then you start screwing up the rotation of each pixel, and you're rotating less here, so you're rotating pretty much nothing, well, nothing at all here, and you're rotating a lot there. So now you get kind of really trippy stuff going on. And maybe if you change this to plus again and take the lines away, it becomes a little bit less trippy, maybe more interesting, I don't know. Then you get still, well, it's very similar to our initial stuff actually, although it's doing different stuff. And maybe one of them should be multiplied so that we get some lines going on and it's easier to see what's going on. U time divided by t. Look at that. Cute, right? So this is kind of just the basic idea of rotating, translating. You can move stuff around if you make a translate function. Of course, translate functions can be done like it's a very easy calculation. So you just add to that coordinate. So you transform by adding a value. Rotation is a little bit more complicated, of course, so that's why it involves the matrix. The matrix is there. Now, resources. I will put some resources on the description, but one thing that you can go check because it's really cool and gives you enormous amounts of inspiration and ideas and solutions is ShaderToy. ShaderToy is a browser tool, so it's a website. Let me switch to browser. So let me see. Let me just go shadertoy.com. Shadertoy.com is a place where people share fragment shaders. So you can see stuff being made here. So these are all like, and for each one, so you have this like smoky one, like the one I showed you before. If you click that, for example, you get it running here. It's running real time. You have the code. You can mess the code up. You can mess the code up, and you'll see the result going on there as well. This didn't change anything. Maybe I just changed the random value. And I don't know if you need to compile. It is compiled. So I guess. Oh no, yeah, there you go. You need to press the play to compile. So you see that I changed it there. If I 0, then bloop, back to where it was. So that kind of changes the background a little bit from black to white. So you get the code. It is not the same as what we're writing here. So because this is so the main function is now called main image, and it receives the frag color and the frag coordinate as arguments. So it will return out the frag color, and it will receive the frag coordinate. So that means that we basically get exactly the same thing. The uniforms are called different. So this is I resolution instead of U underscore resolution. But once you look at the code, knowing that this is the main function, you'll see that it's pretty much the same thing, right? So it's the same language, it's the same thing. So just the names of the variables change a little bit. Here they called it UV, we called it chord, but it's the same thing. Here they do the resolution, but then they take 0.5 out, but that's just to kind of translate the whole canvas right away. So if you understand what we've done there, very simple ways, you can, with a little bit of effort, understand these as well. And the only problems you're going to find are math problems, which unfortunately they are what they are, and and they just need to now at least you have a good motivation to learn a little bit more about it, because you can do really awesome stuff. Yeah, I can leave because the changes don't matter. You can also create your own shaders here. You can play around in the ShaderToy itself. This one is pretty cool actually, and this does has music and everything. You don't hear it, but I hear it. Let me pause that. So now things that we didn't mention is that, of course, these shaders can receive images, right? So you can receive textures as well as uniforms. That means that you could do image processing pixel by pixel. So you can receive textures and then read a pixel from a specific point on a texture and then do whatever, like either directly display that image by putting the pixel on your screen the same color as the pixel on the image on the same position, or you can kind of screw them up and change or do any processing or turn it to black and white, do rotations, distort the image in any way, do translations, all that kind of stuff. You can do it to images as well by just receiving a uniform of a texture and then applying stuff to that texture. The problem is you need to send the texture to the shader, and this GLSL preview does not allow you to send images. So you need another tool. One that I use normally that is super good, that you can send not only images but also 3D models, and it has full support over everything. But I don't have it built. I was actually trying to build it now, but it's just Windows is a pain in the ass to build anything. But it's possible. It's just a way. It's just a matter of fidgeting a little bit with Visual Studio and stuff. But there is one app called GLSL Viewer. If you search for that, that's Patricio Gonzalez. If you see, that's the same guy that wrote the Book of Shaders. So he's sort of an authority in the shader in the community. And he made GLSL Viewer, which is a command line tool that you need to build it yourself, especially on Windows. But it's awesome. It's really cool, and you can send. You can run it with sending 3D models, sending. You can do vertex shaders and fragment shaders. You can do physics-based rendering with it. You can do all kinds of stuff. It's a really nice tool, and it's also pretty simple. You just basically run in the command line GLSL Viewer, and you send and send it as an argument your shader, the one that you want to render. And then it will do all the magic for you. And then, of course, it's super highly configurable, and it's a really nice tool to develop shaders. I use that most of the time, but I use it on Linux. And on Linux it's super easy to install. On Windows, you get the information here on compiling GLSL Viewer, and then on the bottom of everything you have the Windows. It's a very short description, but of course it involves installing Visual Studio 2019, which I didn't have, so I didn't manage to do it. Now I didn't run with the newer version. So, and there's another tool that you also need to download. But basically, if you're lucky, this will all work, and then you have access to just calling that and then just running your shaders in a also much more performance friendly environment, and you can run them full screen and so on. I want to very quickly show you, since I've talked about the Veda tool. So if I just close this one, there is a thing with Veda, is that it sends the uniforms in a different format. So you just need to remove the U's there to get it to work. But basically, if you have installed the thing, you can do Veda toggle, and you go into Veda mode, which gives you this default shader. It's not the one that is running here. You need to watch shader on Veda. If you watch shader, then it's trying to run this shader over here. Ah, wait, you're not seeing anything, are you, Atom? So, sorry. So what I did is that I did Control-Shift-P. It's not working because I'm not. Control-Shift-P, and I did Veda, and then you have the options. And toggle turns it on, And then load shader is Control Enter, that's to load the current shader once. But you can also watch shader, and if you do Control Shift Enter or watch shader here, then it starts just a live shader on the background of your window. And you can also go full screen. Let me see if that Veda toggle full screen. Let's see if that works well with the wow, doesn't really show much. Well, let's first get the shader to work. Veda toggle full screen. Toggle full screen. Yeah, so then you get the code. So if you do toggle full screen, then you get just the shader running, which is nice. The only thing is that now we just get a blue screen because resolution and time are not being passed correctly. You need to call it resolution and time, and then you get errors here. So the errors appear here, and you get some flashing, which is very interesting because now you just need to actually remove it here as well. Remove it here as well. You can also do search and replace, of course. Almost there, almost there. Here and here. And there we go. Now we have our shader running full screen. And you can you can edit anything. So if you say like, okay, all of this, I want it to be 0.0, boom, there it is. And as you code, this is what live coders use. So you can also code this on completely full screen. I guess F11 should take you to full screen. This shouldn't be there. And then they are just coding stuff here. Let me see if I have some nicer example. If I go into, I have this one for Veda specifically, so let's see. I think I used that before on a workshop. Yeah, that is a very cool one actually. Just Control Shift Enter. There you go. So you get a nice little shader, and you can change values and get different results. Actually pretty crazy results because I'm changing numbers very, very aggressively. So there you go. So you see what's going on in there. Like here, and if you do 2, then you get even more weirder result. There you go. And this is actually a shader that I started and I kept working on, and then applied it to my kind of the front page of my website, which is basically just a shader actually, and just links to the social networks. I don't really have much on my website, but to see how this runs on a browser, you can just go to, let me just switch to browser then, and if I go to David Jonas, then you can see that it runs fine on the browser as well. This is actually a version of that shader that I just showed you on Veda. And it reacts to the mouse position because I'm sending the mouse position as a uniform. There you go. So, and you see that it runs pretty fine, and it also runs on your phone, on mobile. And if you have a modern browser anywhere, or you have a modern browser with WebGL compatibility, it can run shaders. So that's pretty interesting stuff you can do on the web that you don't see so often. So that's one of the nice things about shaders, is that you are free to just run them everywhere. There's an app on your phone as well that is called, on Android specifically. I don't know if there's for iOS. I'm not an iOS user, so I don't know. But there's an app called Shader Editor, I think. Let me see what it's called for sure. Shader Editor, yes, Shader Editor. Yeah, it's called Shader Editor, and what it does that it's pretty much the same thing as Veda. Say that you have the code. You need to code on your phone, of course. And then the shader is running on the background. And as you can get pretty complex shaders with images. You can send textures. You can use all the stuff from the phone, like the accelerometer, and so you get all these uniforms sent to it, which is really nice. And then you can generate live wallpapers with it. So actually, most live wallpapers are actually fragment shaders running on the phone. So even the ones that come by default, they're just shaders running in the background, fragment shaders running in the background. So you can of course toggle code there. You can also make it interactive by receiving the touch input, all that stuff. So that's pretty sweet stuff. A lot of stuff to explore in this. I can maybe make it bigger because yeah, so you can see this type of stuff you can do, and then make it into a live wallpaper. So that was sort of intense and weird and a bit scattered as well, I suppose. How do you guys feel about it? Was this useful? Did it open up some doors for you? Sorry, Boris, you need to repeat that because my sound was off. Cool, nice. Yeah, so I don't expect that you guys are going to be now all of a sudden, oh yeah, now I know shaders. No, of course not. Shaders is a whole new language, is a whole new way of thinking. So it will take time, but hopefully this is like an introduction, so you know how they work and you know how to make them. And even when you're working with much higher level tools like Unity Shader Graph, that it gives you a little bit of an understanding of what's happening behind, at least. Yeah, I'm not sure how to adapt this lesson to the future. I haven't done it in the past in this thing. I've done always only Shader Graph, but I thought like, yeah, let's give it a go and actually explain a little bit about the GLSL. So I'm not really sure yet if this is a good idea or if it's just confusing or if it's just boring or if it's so I'd like some feedback from you guys, and I also need to of course improve the content a lot, so there's a lot more we could do with our time, and I could move much faster in some areas and a bit slower on others. So but your feedback is always welcome, of course. And I see really cool stuff coming up on the Discord channel, so that's really nice, really cool. Yeah, ShaderToy in some cases can really crap up your CPU, well, your GPU actually, but then the browser can consume immense resources. But it has a lot of cool stuff. Look at that, and river. Nice water shaders are, of course, classic as well. That's pretty good. And pretty simple as well. So it's very small. Most water shaders are made like just by rotations actually, and Perlin noise mostly. So cool. You guys didn't see any of that, right? Because my scene switcher is gone to hell. So what? Doesn't matter. It was the water shader that's on the front page of ShaderToy. So Shader Graph, we still have half an hour. Maybe we should go very quickly through it. let me just set up my environment here. Don't save. And let's exit this and exit that. So let's just have a very quick look at shader graph. Let me see if Unity comes up in here. Wait a second, I'm just opening it up. I'm just going to do screen share in this case. There we go. Oops, sorry, I'm moving the wrong window. Let me just fix that. Yeah, there we go. So we got Unity. I'm going to add a new project. I'm going to create a shader tests. Not add. Sorry, a new project. My brain is fried. Shader tests. The shader graph. I'm not sure. Like now in the latest version, I think it's available as a package, and you can install it even if you go into normal 3D or 3D with extras, maybe. On earlier versions, it was only available on the high definition RP or the universal render pipeline there. So let me not put it here because this was Floris's work, so I'm just gonna put it here. No, actually not. I'm gonna put it here. Storage. Unity. Okay, I'm just gonna put it here. Projects. Very few on this one. Select folder. There you go. Just so that it's on the right place. So then I'm gonna go for the universal render pipeline because I know that has access to or high definition, but it takes longer to load. So I think it's fully supported there as well. So I can create. You can also go for the high definition if you want. It just takes longer to load, I think. It's a little bit annoying. There we go. Need to wait a little bit. Is there any questions and comments? Anything that you guys want to say while we wait for the loading? No, I had the universal render pipeline. But you can do the high definition as well. I'm not sure. I think the 3D with extras will work, but I'm not 100% sure. I need to try that. But I think it will work. You just need to add the package on the package manager, but the shader graph package. But on the universal render pipeline and on the high definition render pipeline, those come already set up. So let me see if now Unity works like this. Yes, it does. Let me just make sure you see everything. So I did the universal render pipeline. So you get this scene, like the default scene. I'm just going to remove the example assets. There's a post-processing volume here, which, okay, well, it has these basic stuff in there. That's good. Tone mapping, bloom and vignette. Maybe the volume is a little bit annoying, but well, doesn't matter. So let's see. Let's see if everything works basically first. If we go here and we do create new, and then there is shader, and then we have the graphs here. So we have the unlit graph, the PBR graph, and the VFX shader graph, and the subgraph. So we have all these options here for shader graph. The most generic one and the one we usually use is the PBR graph. So that's physics-based rendering graph. You don't see my context menu either. That is really weird. I'm gonna go into screen share mode. Okay, so what I was doing is going here and going into create. This is very small, I guess, for you guys, but that's fine, you know how it goes. And then here there's shader, and then here you have your graphs. And I'm going to choose PBR graph, which is physics-based graph, physics-based rendering graph. And it creates a new shader, and I'm going to call it test shader. And then if you double click it, you should get your graph. Let me just maybe maximize this. You get your graph. So that's node-based rendering. Let me just go back into unit full screen here so that you can see it better. It's bigger as well. And I'm going to move my face off of the preview so that you can see the preview there. So there's a little ball here that previews what that shader is going to be like on a sphere, but you can also just do a capsule, for example, and then you get a capsule. It's just a preview of your shader. And there's a few things. So there's your main node here. So we're working on a visual programming language. This is going to be much simpler than the other one, but is also yet again another different concept of programming. So this is all about inputs and outputs. So all these things, all these little dots, they're inputs, and you can it's like you can imagine it as these old telephone centrals. You probably have no clue what I'm talking about, but there was before, like phone connections had to actually be manually linked together. So they had these big things with cables that they would put a cable that connects from one to the other. They're basically just sound jacks, you know, like your headphone jack. So this works the same way. You're just going to connect lines from one point to another. So from one output to one input, and then you can just keep doing that. And this one here, the PBR master, is the one that is going to output to your object or to your texture. Basically, you're generating a texture here. But not only texture, because you have also access to the vertex position. So this will mix vertex shaders and fragment shaders. So you can do both. For example, a fragment shader would go here into the albedo, and the albedo is basically just the color of the thing. So whatever you put in here, plug into here, then it will affect the color of the object. If you do the normal, then it's going to affect the normals of the object, so you can do kind of noisy normals in there, for example. And on these vertex position, normals, and tangent, these are going to affect vertices. So and then of course you have the physics-based settings here. Like if it's metallic, this is how the light will affect the object. So how metallic it is, how smooth it is, the occlusion, the alpha, and the alpha clip. So so these are all settings. They're like the settings of the material that you have on your material inspector normally, right? But now you can sort of code them and add new nodes and pass them through to these inputs here. Another thing you have is this little thing here, which are the properties. And the properties are basically the uniforms. So that's the uniforms that you're going to send to your shaders. So so if you want to be able to either by hand on the inspector or by code to send information to your shader and to change information on your shader, for example, colors or something, then you can add properties here, and those properties are going to show up on the inspector to be edited, and you can also edit them on your scripts, so that you can make your shaders react to your code. So let's see. This works pretty much by just creating nodes. So there is a way to create node directly by just positioning your mouse on a place where you want your node to be. By the way, if you want to navigate in here, if you press your mouse wheel or your middle mouse button, you can pan, so you can move this around. If you scroll, you can zoom in and out. So you can kind of generate space for your nodes to be. If you position your mouse anywhere and press space, it opens up. I need to go into screen share mode again, or else you don't see stuff happening. Screen share there, and I'm going to maximize this. It's a little bit smaller, sorry about that. And I'm going to take my webcam out of the way, put it here. But like this, you can see the actual context menus, or else they don't appear on the stream. So if you position your mouse anywhere and press space, you get this create node, and then you can search for a node. And then, or you can just browse them here. So if you go, for example, like procedural, oh, checkerboard, that's interesting. And then you get a checkerboard. So the checkerboard is just a fragment shader that will just make a checkerboard pattern, right? So, and then you have a bunch of inputs on this side and outputs on that side. So there's only one output here, and that's 3 means that there's 3 values coming out of here, so it's a vector 3. Or in this case, it's like the color output of this thing. And if you click this thing and drag, then you get a little line coming out of it. This line you can connect to these dots over here. So there are, of course, different types of input and types of output. So what you want to do here is look at the color of the little balls. So this yellow ball means that it can connect to any yellow balls. But of course, it's also possible to connect to other balls that have lower amount of values. So in this case, you have 3 values here, so you can connect to albedo, which is a color with 3 values. But you can also connect to metallic, and then only the first value is going to be used. So let's just connect it here to albedo, and you see immediately that it changes, and we have a checkered pattern on our color. Like I said, the albedo changes the color of the material. So now we're changing the color of the material with this shader. And that's pretty much it. And then, of course, now you can select these colors over here. So for example, if you want a real checkerboard like black and white, you just set this color to black and set this color to fully white, and then you get a full black and white checker pattern. If you can test it on a cube, for example, and then you go like, oh, nice. Yeah, it of course depends on the UV mapping of the object. You can also upload your custom mesh if you're going to use it on something something that you've created or that an artist sent to you. So then you get a checkered thing. And this here is the frequency. The frequency is basically how many squares you get, so it's the zooming. So if you do this, you get more. If you do that, you can just do really a little bit more. So if you put, let's say, 5 by 5, then you get correct tiling there. So then you get a checkered pattern. There you go. And then you have a shader that just outputs a checkered pattern, and it's going into the color. But, for example, you can also, of course, do maths, and you can multiply colors. For example, let's see if we can make, for example, let's see if there's a gradient. Oh yeah, there is a gradient. So let's make a gradient. And let's choose some colors here. So it's red, and this color over here. Let's do something green, something ugly. It's always good to do something ugly because they're clear to see. So now we have a gradient that goes from red to green. And you could, for example, multiply this output by this gradient and then pass it to the albedo. So then if you go here, and let's say if we can multiply things, press space and say multiply. Okay, let's multiply that. So it receives 2 inputs and it makes 1 output, of course, right? It's a multiplication. So let's see if we can plug this one in there. Probably not. Oh, wait a second. This is not allowing me. I'm sure. Oh, it doesn't allow me because this is a gradient output. So the outputs are not compatible. So we need something in the middle. Or actually, let's just choose a different one so that we make it simple because we have very, very little time. We have 10 minutes. So I'm just going to do maybe Fresnel. There you go, because that is a type that you can multiply easily. So that is just like a sort of a gradient type of thing. And now this one you want to disconnect and you connect it to here. Now you get like a mix between these two, and you can kind of make it a little bit more intense here. And then you can do the out and it goes into the albedo. There you go. Then you get something weird, right? So that it mixes both of them together. This probably is better seen on a sphere. So you see that now the sphere has like a darker spot in the center. This is actually nice to, if you don't mess with the UVs, this is actually nice to make like glowing stuff. The Fresnel effect is really nice to do glowy objects and holograms like you so wanted to do. Let's just add a property so that you can see it working. And I'm going through this really quick, but actually let's save asset. And let's try it first so that we see it working. So now if you go back to your scene and let's put in there a sphere on our scene. It's until 2:30? Ah, yeah, because I thought it was until 2. I forgot. The schedule changed. So we have a little bit more time. That's good. Let's go. We can play a little bit longer. Actually, I should have left some time for you guys to experiment with the shaders, but I saw you guys were doing it anyway, so that's fine. And this way you have a little bit more compact information on the stream that you can watch again later. So now we have a sphere. And you can just on the material properties, you can create a new material for this. And let's say our test material is going to use our shader. So then when you go here into the shaders on the material, you have a graph, shader graphs here. And if you go into shader graphs, you have a few of them that are already there pre-made for you, and whatever you create on your assets is going to be here. So you can switch it to test shader, and you see that you get the little ball there right away. And you don't get a lot of settings here, just the default settings. And now you can apply your material to the ball. And now you see that you have a ball with a Fresnel and the checkerboard. Right? So that's how you apply it to Unity, right? Now let's try something a bit more interesting. Let's go and do, for example, let's mess up this position over here. So if I do here and do a vector 3, and I'm going to output this vector 3 here to the vertex position, then you get like nothing, right? Because all the vertex positions are now on 0, 0, 0. So you have all the vertices in the same spot. So you've just moved all the vertices to the same point. So you don't see your object anymore, right? Then, if you want to affect that, let me see if I remember, what was it called? So you have the UV. Let me see. UV. As a 4. No, that's not the one. Oh, I forgot which graph it was that would do this really easily. Let me just take that off. I can get the vertex position. Is it vertex something? Vertex color, invert colors, no. Transform. So this is rotation, translation. Cool. Object space. Was that it? I forgot. I haven't worked with this in a long time. Let me just delete this one. And I want, because there is one to get the current object space. Let me see if that works. Let me put this bigger also so you can actually see what I'm doing. And then I can zoom in, of course, and then you see much better. So I want to plug something in here, but I want to have access to the original object space, but I don't remember which node it is. That's one of the problems. I think that is it. So if I put this one here, no, I still don't get it. So that's not the one. Well, I don't remember. That sucks. Let me try. Position, is this the, yeah, maybe. World position, yeah, maybe it is. Let me see. Yes, I think, well, it did move it, but it moved it on a, okay, that might be it. I'm not sure if that's the one. I'm gonna close this because it doesn't mean anything, that preview. Okay, well then let's see. Then let's add. So we're gonna add 2 values here. Oh, this is a 1, yeah. So no, there's a vector 3 add. Let me see if there is an add that receives 3. Add, no, there's only 1 add, so I think it will adapt to whatever I try to do. So if I do add this one to this one, and then apply that one here to the vertex position, then we get exactly the same thing because we're adding 0, but then if we add 1 here, then it goes up, right? So that's what I wanted to try. Okay, that's what I wanted to show, is that you can affect the position of the vertices. So let's say this shader is for a little power up. And then what we want to do is then we do the cosine. So of course we have the cosine here, and the angle comes in here, so it goes from black to white, of course. Let's put 0. And then in here, let's put time. Oh, actually, we have the cosine of time directly here. That's even better. So we don't even need this one. Nice. So let's say that's the cosine of time. We're going to put it here on y. Bloop. And look what we got. We got a ball that goes up and down. Cool. So that means that now you can get the GPU to do a type of movement without having to calculate every position, every frame. The GPU is doing all these calculations for you. So if you save this asset, and this can be really powerful. Let me minimize this. And if you go into your scene, you see that our little ball is going up and down. So you get your, actually, especially if you put it play. So when you're on, when you're not on play mode, then your image only updates when you move something or on your pan. But now you see like you have like a little power up that goes up and down. You got a couple of errors here. I don't know why the shader moved. It's just a vector type difference. It doesn't matter. So you can see that you get this going up and down, but of course the CPU is doing nothing, so the sphere is always on the same position, so the position is not changing. It's just the rendering that is changing. So it's rendering it up and down. Actually, its collider stays on the same spot. If you go into the scene view, and if you check the collider, and you see the collider is actually there. So you see we're moving it a little bit far, so that's kind of a screw up there. So imagine this for power-ups, the amount of CPU time that you would save just by making them bounce up and down like this instead of putting a script on them that calculates every frame and sets the transform, the position, to go up and down. So you would put all that work, especially if you have 1,000 of these, because now you can have have as many as you want and then just move them around, of course. And they're all going to be doing the same thing, of course. Of course, now they're all doing the same movement, but of course you could go here and add a random here. So let's say random range. And random range between the minimum of 0 and the maximum of whatever. And you just plug this one. You plug this one. Damn it. Plug this one into. Well, I need them add. Let me put it big again so you guys can see what I'm doing. Maximize, zoom in. So now I'm going to here do another add. So I'm going to add to my cosine, or actually to my time. I need to add to the time. So my time is going to enter here. I'm going to add a random number to to my initial time. That's what I wanted to do. So that's a little bit weird. Well, it doesn't matter. So that's gonna be weird actually. Let me just put it here. I'm just making it up as we go along, so that's why I'm kind of going back and forth. Just trying to come up with simple examples, but not always that works out. So I'm actually adding the time to a random number, and then that out goes into, let's calculate the cosine. If you actually drag this out, that's also a nice way to get a new node going on. So let's do the cosine of that, and then that goes into here. And I guess that's doing what I expected it to do, but I'm not sure, because maybe the seed is... what do you mean? Change the space on the position? It's on world position. Here, object position. Oh yeah, that's what was screwing up the collider actually. So that's good. Thanks for that. I didn't see that we were in world position. So so let's see if that actually does what I expected it to do. I'm not sure. I think not likely, because I think the random number is not being thrown every time. Let's see. So they're still all doing the same thing, because the random number is not being so the seed is always the same, so then you don't get different behaviors on each one, but okay, you get the point. It's much nicer if you guys are exploring things, and there's a million tutorials online to do this, whatever you want to do, because people are playing with this a lot. But this is the idea, and you can do a bunch of things like play with each vertex with each vertex independently, so that you kind of add noise. There's Perlin noise, of course, directly here, or noise actually. There's gradient noise, simple noise, Voronoi. So you have a bunch. This is like cell shaded noise kind of thing, which is quite interesting, that you can make move. So if you have this going on, let me see if I can get another one going through here, for example. Look at that. That's pretty cool, right? And then you can, for example, let's replace this one. If you delete this one here and you put this one here and do the out into EA here, then you get a nice little thing there. So you get these. Maybe we just put one and one so you can see it better. So now you see like little cells going on in there. You can use that on the normals, for example, and get a bunch of interesting kind of bumpy stuff on there. So you just need to explore the nodes that you have. So when you press space, you get this is basically everything that you have to work with. And then for properties, that's the last thing I want to show you, and then we go through the whole workflow very simply. Is here you just add a property that can be any of these things. For example, the simplest will be like a color, and you can call it main color. And it's exposed. That means that it will appear on the. Oh, I cannot. Wait a second. That's not what I wanted to do. Oh, damn it. Let me add it again. Color. Main color. And let's say the main color would be like this white here. So then you can just drag it out from here and put it here, and then you have a node of that color that goes into here. And now by default is black, so you can default it to white. Then you get white. But now you have this extra possibility when you save the asset and go back to your game. On your scene view, now when you go into the material, you have a main color setting here that you can set, and you can also set it independently per object as well. So if you do this actually it's setting on all of them. Of course you need to create different materials, so you can create a different material with the same shader and then set it per material, let's say. So you see that here you can, and then of course these you can also set with code, and you need to keep in mind that when you set in code, the one tricky thing to figure out is that you need this reference here. So this generates a reference. It generates it randomly. Do you see it well? No, definitely not. Let me see if I can go to Unity. Is this any better? No, because it's very big. Let me see if I can make this bigger for you guys. If I make this smaller. Yeah, there you go. So this is bigger so you can see. So there's this reference here. And this reference is what you're going to call in your code. So you remember when you're setting the color of a material, you do set color, and then you have to name the color. So that's normally the main color is underscore color with a capital C. If you want to set this color, then you have to use this reference. You can also change it here, and you could call it main color, for example. Or you put an underscore on it, for example, like the normal, when you set the normal material. And then that reference is saved, so now it's called main color. And then when you want to set it in code, let me just go back in here, and let's remove all these others. Let's keep just one, focus on it. And then let's put a new script on it. Color, you don't see this, but I'm just adding a new script. Changer. And it's thinking is going to appear there. So now we have a color changer script here. I'm going to open it up. Just give me a second so that the editor loads. Let me see if that appears here. Luckily enough, yep, there we go. We have code. Close this, increase the size a little bit. So, so now what we're going to do is that, well, let's make something trippy. Let's say color C, and then C will be equal to random dot color HSV. So it's going to give us a random color. And then if you want to set that on the material, you need the material. So material underscore M. We should have called this underscore C just to be consistent. Underscore M material, and then the material will be equal to the get component, and then you need the mesh renderer, and then you need the material. So that's the material. And then here on update, or actually let's just set it here on start. And then you go to m.setColor, and then you need to put your reference here. So this is the reference from your shader. So we did underscore main color. If you didn't change it, you would need to put like the weird number here. And hopefully that will work. And then you put that color in there. It is still complaining that the main color, no, it's just string based is inefficient. That doesn't matter because we're doing it on start. So now we need to stop this, and let me go back to Unity. So now we've compiled. Something is taking up my... okay, no, it's just the updating of the shader. So now it is not changing it at all. Do we have any errors? Did we put the thing in there? Wait, I put the script on one sphere and then I deleted that sphere, so that's bad. So I need to add this script again. Actually, I'm just gonna do the color changer. But no, not on play mode. There we go. Okay, now we have the script. So now if we play, we got pretty much a black color. That kind of sucks. Let's try it again. So now we have also still a very dark color, but a little bit more red. So we're getting really dark colors. Actually, I think also that our shader shades them really dark. But basically, it's changing the color. So it was black and white, and then when you play, it becomes some other color. Every time you play, it's a different one. And actually, if you duplicate this, you should get a different color, I guess. And yeah, so different color. If you duplicate it again on start, it will give you a different color. If you duplicate it again, then you get a different color, and so forth, right? So now we get some variety enough. There you go. So then you get different colors set in code. Questions? Hello? Do I have audio? Maybe I'm missing audio. No, but there's no one talking actually. Yeah, so I should be good with it. Yeah, so that's actually very like very quickly just going through the workflow, and that's and the slight like just touching the possibilities of shader graph, of course. But that's how you use it. That's how you set things in code. That's how you maybe make things move. That's like the only kind of little useful tip here, that if you want something to move in a very specific way and you don't care if their colliders are always on the same spot, this would be the typical example for pickup items that you want to be floating around. You can save a lot of performance by putting all that work into the GPU instead of the CPU, right? And then of course, like water shaders, you can make a million different things, materials for like walls and stuff, that instead of relying on a tile based thing, you can rely on a generative thing, as for example, like using Perlin noise or gradient noise or stuff like that to generate the texture in the GPU procedurally, instead of relying on an image. So I was just getting a call from Mark. I'll need to call him back. But basically this is it. And then I'll just want to give you a little bit of time still to play around and to test it out. And of course just Google Unity shader graph and you'll get a million ideas of stuff to do with it. So I'll call it. I think we are we've covered more than enough. Was this what you expected from the shader class? This is as much as I could pack into the time we had. But at least I think you got an overview. But I'd like to hear it from you, what changed and how you feel about the class, so that I can adapt it for next year. Yeah. Cool. Yeah, nice. That's very nice to hear that it was useful. You mean that you wanted to see more examples, right? So in that case, I will add a bunch of resources to. Well, I'll put them on the resources chat, but I'll also put them on the description of this video so that you will be able to see it when you watch the recording. I'll need to edit the recording a bit, like cut out all the waiting times, because I left the stream on while you were having the other class. So it will take a while for this one to be available. Also, it's 4 hours of stream, so it will it will take some time to process. But I'll put it on the description, a bunch of links to all the stuff that I've mentioned, to the shader toy, to the tools, to the GLSL viewer, to Atom, to all that stuff. I'll also put some more links of stuff that are interesting, like examples and cool stuff that have been done with shaders in general. And so then you get a bit more examples, right? Now that you know more or less how it works. Of course, we didn't touch vertex shaders. That would be quite important to go through as well, so you might want to have a look at that. And how they connect between vertex and fragment shaders. So that's it. This class will be put in YouTube, and it will be unlisted, so you'll need the link to access it, and I will put it on. I will put the link on the resources as well, on the resources chat on Discord. Nice work, Evan. That looks really cool. That marble ball, very cool. So Dimitri just shared. Oh, rivers. Nice. Yeah, those are cute. Ooh, nice stuff. Yeah, maybe we. Yeah, I'll check the schedule. Maybe we can do a little bit more on shaders. Maybe we could fit one more class to kind of just also to kind of go a little bit deeper and just look at examples and things like that. That would be interesting. So I'll stop the stream. I'll still be on the chat on Discord for a bit, so that we can talk a bit more if necessary. I'll have a call with you, Dimitri. I'll have to have a quick call with Marco because he was trying to call me now. So I'll need to check what he wants. But I'll have a chat with you. Also, we can do it in the development chat as well, in the voice chat, and then we don't have the annoying 5-second delay. So I'll call the stream here, and I'll switch to the Discord chat. So end stream.